Hello everyone, this is Alan. Sorry for the inconvenience that I cannot attend today's meeting in person to present a presentation with you and discuss with you guys. So if you guys have any questions about my presentation, please feel free to contact me and message me, and we can have further discussion. So now we are going to focus on the scalar theory and vector theory, which is just as another method for us to solve the electric field. From the chapter 2, we know the K surface, and all we're trying to do is to solve the K and then plug it back into the wave equation to get the corresponding electric field. Here we introduce the scalar theory and vector theory. However, for the scalar theory, we ignore the polarization wave, and also we assume the material is isotropic, so which is a simpler version. And where the vector theory is an isotropic material will take place, and we will discuss it later in the class. For the scalar theory, first we use the wave equation, and then plug this equation. We can rearrange the wave equation, and note that for delta sigma refractive index, we have this kind of relationship. This can be easily shown that this kind of sense, okay, this, which indicates that delta epsilon r equals to 2 delta n epsilon r. Again, kind of think in this way. So we will get this kind of relationship. And from the Bragg diffraction, that part about the acoustic wave grating, we know that we need to have away the momentum conservation and energy conservation. So in this kind of sense, the scalar theory comes in. And just as previous discussion, we know we only consider about a harmonic wave. Thus, we have this kind of form, which CC stands for complex conjugate. So now we will just plug in all we have, that we know the electric field contains of the incident and reflective, and also we plug in delta L, which we obtained via during the last lecture about the acoustic wave equation. Just take into a strain S into consideration. We have the vivid proof about it, right? Delta L and the L. Also, consider a slow vary envelope approximation, just as the Gaussian beam. Just as what we have learned during the Gaussian beam, and also the energy conservation. Then just all these conditions combined together, we will get the coupled equation stated as here. Okay, so note that for sub EI sub DLI, we get the reflective index, reflected electric field. While doing we found the reflected electric field with the relationship with the incident electric field. So we define a coupling coefficient in this way of form. So still, energy conservation, momentum conservation makes us to further derive term here. So with that, our life just becomes easier, such that we have a simple relationship between the electric incident and the reflective electric field. So plug it in, plug these into plug trying to find incident and the reflected electric field. We thus found the L term. We defined it to be crystal length. And in here, this kind of tells the story about the theta b, where we will found that with the larger the theta b is, the smaller the electric field is, the smaller the power is. And with larger theta, it actually corresponds to larger m. If you guys still remember for the Bragg diffraction, it's kind of equals to m lambda for constructive wave, for constructive interference, because consider this to be, and then you have a wave incident theta b. So what we're trying to calculate is this. Okay. And it's kind of reasonable for us to have an initial condition in this way, because at first we just have an initial incident wave, but there's no reflected at all. And assume the theta b is small enough, that is cosine theta b is equals to 1. We have the following term. And energy conservation, kind of reasonable. We know the energy, the Poynting vector kind of stands for it, and it can be kind of approximated this way, actually. So this kind of form gives us the energy conservation, because they are all in the same medium. And just recall all what we have for, we will found that there's a periodic distance, and it's literally this one, because just plug this into here, you may found that it's kind of a standing wave, just periodic distance. And actually, when we are considering the total electric field, the incident and reflected, we assume the polarization of the coupled fields are in the same direction. And this is why we can ignore the polarization in the scalar theory, just as mentioned at the beginning, very beginning. And now, with the scalar theory, now we are going to talk about the more general case, which is the vector theory, and it can be applied to an isotropic medium. So same, just as the previous lecture, actually in the previous lecture, but the last person just talked about the strength for acoustic wave, for us to further another perspective to understand it. The strength propagates in medium as acoustic wave. Yeah, and we have the displacement vector, we have the equilibrium location. Now, the definition of strength is defined in this form. And it's second rectangler because it's related to J and I. And this is kind of obvious that it's symmetric. Thus, for a 3x3, when I found 3x3, there's only 6 types of it left, because this equals to S21, this equals to S31, this equals to S32. So actually there's it can be kind of categorized into 2 types. That one is it oscillates in this way, another is oscillating this way. Okay, and just re-emphasize, acoustic wave is a propagating strength, and there are some possible acoustic wave propagating along Z, and these are all the stated possible circumstances. So actually, for the vector theory for using a vector theory, it's kind of important to know that the molecular displacement will change the refractive index through the photoelastic effects. Thus, the index ellipsoid is having this form, where we just plot this is literally just ij, and we just plug the initial plus the delta. And where the P just form a photoelastic tensor. And just as mentioned here, we have S to be symmetric. And we also have N to be eta to be symmetric. And thus, 6 by 6, we have P to have 36 independent elements. So for an isotropic medium, the P can be expressed in this way. Whereas for isotropic case, it's literally this kind of relationship, and it's kind of obvious. And continue the concept for acoustic wave. It's longitudinal wave. We can express it with the place it is, and with the frequency taken into consideration. We can thus having this kind of form for our eta tensor. Actually, just the delta eta. And thus, the impermeability tensor becomes this kind of form, where you may find that this is different for the others. And this term would suggest that it makes the isotropic material uniaxial, because these two remain the same, but these just be a difference maker. And this is what exactly the uniaxial means, where definition of a uniaxial. So this is also what we have defined in the acoustic wave, just as the previous person just mentioned. And so we just plug with the solution we have obtained before, we will get the reflected electric field at the crystal length to be this form. And just to reiterate it, and also the merit of field silica, these are all what we defined during acoustic wave, and we have just shown that this is equal to log v square s square, where s not. Yeah, this is what we get. And this is dependent to your material, because this is the density of your material. So with all the electric field being solved, we now can define the diffraction efficiency. It's kind of reasonable to us to divide it to have electric field divided by the intensity of the reflected wave over the intensity of the incident wave. Thus, we have the following relationship. And if the L is given, then we need the acoustic intensity to be this far to achieve 100% reflection. It's kind of you just plug it into here. Like it's m divided by m and lambda 2 and 2 and L squared, just both divided to each other. Yes, and then you'll get the 100% reflection. So this is all about the scalar theory and the vector theory. So back to our here. So for scalar theory, we start to have a basic concept and we define some stuff. And for the vector theory, it's just the most general case. You can see like how the acoustic wave made an isotropic material into a uniaxial material. And for the uniaxial material, just think of the case surface. For the case surface, it's basically in this way, which means that for any kind of direction, it will always see an ordinary refractive index and an extraordinary reflected index, which is at the ellipse. So this is all for the week 5 notation, week 5 presentation. So starting from the chapter 2, where the case surface take place, and then we have the overview, and then we have the basic concept about the case surface, which means for a specific the all possible spatial mode for a specific temporal mode omega. And then we start to introduce the acoustic wave, which is acting as a grating. And then it also has some Gaussian beam effect and the Doppler effect. And these we consider to be really small. And thus, we kind of get to the point. Let me check a bit. Yeah, we kind of take into a concept about the Bragg's diffraction, and we also need to take into consideration about the energy conservation, the momentum conservation. And with all these tools, now we start to, and of course we define the strength during that part. And last, just the scalar theory and the vector theory, where we just combine all the stuff together, trying to achieve our ultimate goal to solve for the electric field. And with the electric field, we can now know the behavior during inside the material, whether it is isotropic or anisotropic. And the difference in this chapter is that we introduce the p vector, and this p having 6 by 6 independent elements, and these different elements, and it just shows that how an acoustic wave make an isotropic to be uniaxial. And that's all for me. And hope you guys enjoy and have some takeaway from this lecture. If you have any questions or anything you would like to discuss with me, please contact me. I'll be really happy to have you. And that's it. Thank you.